Hi astronomy students, this is Miss O'Rourke. We are finishing up how stars are born and talking about where their energy comes from. Alright, so source of stellar energy. If you remember that when we talked about the sun back a couple chapters ago, we said that the sun produces energy by fusing hydrogen into helium, and this happens through the proton-proton chain. Right? Two protons come together, gives off a neutrino, gives off a positron, becomes deuterium, which is a isotope of hydrogen, bombarded by another hydrogen, gives off another gamma ray, becomes a isotope of helium, but it needs to bombard itself with another helium of the same kind, gives off two hydrogens, and becomes a helium. Alright, so many stars are going to make their energy the same way that the sun does, using this proton-proton chain. However, the CNO cycle, the carbon-nitrogen-oxygen cycle, is much more efficient. However, it requires a much higher temperature than the proton-proton cycle. Both of these processes are going to do the same thing. They're going to take one helium and add it to another helium, they're going to take one hydrogen, add it to another hydrogen, add it to another hydrogen, and add another one in, and make helium. So stars have to be slightly more massive, and they have to have much higher temperature in order for this carbon, nitrogen, oxygen, or CNO cycle to happen. Stars that are more massive than 1.1 solar masses can use the CNO cycle, and then the less massive stars are the ones that have to use the proton-proton cycle. And this just takes you through. Carbon adds the hydrogen, becomes nitrogen because it's adding a proton, right? The proton, or the nitrogen, breaks down into carbon-13, releases a positron and a neutrino, and then it's bombarded by another proton, which then becomes nitrogen-14. That nitrogen-14 is bombarded by another hydrogen, which becomes oxygen-15. Oxygen-15 gives off a positron and a neutrino, which ends up becoming nitrogen-15. It's bombarded by another hydrogen, which becomes carbon-12, or gives off carbon-12, and then the helium. Okay, so energy transport. How is the energy transported in the stars? Well, energy generated in the star's center, that's where all the energy is coming from, has to be transported to the surface in some way. Okay, so energy is going to flow from the hot core to the cooler surface as either radiation or convection. Okay, conduction is not really used in the stars, but convection is used because is important in its use because it not only moves that energy, but it also mixes and stirs the material. Okay, so in radiative energy transport, you've got just the actual energy that's coming and radiating straight out. Now, sometimes it comes through in the forms of gamma rays, gets bombarded through all these little collisions here where it's being absorbed and then re-released. And when it's re-released, it's usually given off in a lower energy level, such as not just gamma rays, but you've got your X-rays, your UV, your infrared. Sorry, my alarm went off. Okay. And then you have your outer layers, or most of your stars use your inner layers this way, and then your outer layers would be your convection zones, which is where it's stirring and mixing the gases. The hot gas rises and the cool gas sinks. Okay. Cool gas sinks. Alright. Let's see. The upper, I think this is the one I need. I need the law of hydrogen. Okay, let's talk about this. Okay, so our sun is going to be one of the main sequence stars. It's kind of on the lower main sequence because it's cooler. It has a radiative zone in the middle, which is the core is where it creates its energy through nuclear fusion. It uses the proton-proton chain. It makes the energy. The energy is then given off through radiation until it reaches the outside When it gets to the outside part of the sun, or the photosphere, this is where convection takes place. And the convection is where the hot gases rise and the cool gases sink. Okay? So you've got your nuclear fusion in the inside, your radiative zone here, and then you've got your convection zone here. And most of the stars follow this path with their energy transport. Okay? As you go from the core to the outside of the sun, the temperature and the density and the pressure is actually getting lower. Okay? The temperature here is really high. As you get further away from that, it gets cooler until you reach that outer layer. That's when it heats up again. The density here is extremely high. As you get out further and further, there's more space, and so it gets lower. And then the pressure, of course, with the temperature being lower, is automatically going to be lower. Okay, so any stars that are approximately 1 solar mass or less, which is a good majority of the stars, will follow this same, have the same structure and follow the same energy transport. Alright, so hydrostatic equilibrium. Alright, hydrostatic equilibrium, it says imagine that a star's interior composed of individual shells. Okay, within each cell, two forces have to be in equilibrium with each other in order for this to maintain its structure. And this is called the law of hydrostatic equilibrium. It says that the weighing down pressure on a layer of gas must be balanced by the pressure in the gas. Okay, so the weighing down will be the gravity. Gravity is pulling down, and then the inward pressure that's pushing outward, they have to be equal. Okay, now remember that pressure that's pushing outward is there because of the temperature on the inside, of that star. What else? Sorry, all sorts of noises in this one. Okay, that shows that the inner layer of the stars must be hot. They've got to be a lot hotter because they must support that weight. In order to get that pressure there, you have to have that heat or that temperature. If that temperature's not there, the pressure's not there, and then it falls in on itself. Here's just some more about it. Outward pressure force must exactly balance the weight of all the layers above everywhere in the star. Okay? And that's what helps to build the interior of the star. And this is why we find stable stars on such a narrow strip in the main sequence on the HR diagram. Okay, so here's the HR diagram. Narrow strip. Here's all your stable stars. And that's a good majority of them are right here. They have to have a perfect balance. A perfect balance. Okay. Energy transport. So the upper main sequence stars, these here, are way more massive. Okay. They must be hotter inside, and that allows them to use the CNO cycle, the carbon, nitrogen, oxygen cycle. And this cycle is so sensitive to temperature, the energy production occurs in a small, teeny tiny region near the very center, the core. See how the core is teeny tiny compared to the rest of the star? Yeah. And that teeny tiny center is going to be your convection zone. Okay, and then the outside, the big part of the star, the outside, is going to be the radiative zone. Okay, well then on the other end of the spectrum, you have your lower main sequence stars. Okay, the lower main sequence stars are less massive. They're not as hot inside. They fuse hydrogen using the proton-proton chain. The chain's not sensitive to temperature, so the energy that's generated is more widely spread throughout the core. Okay. Where am I? Oh, there it is. Okay, so it's got a little bit larger core, and it's going to be radiative zone in the core, and then the outside is going to be a convection zone. And then the lowest mass stars are so cool, their gases are opaque, and they are pretty much convective zones all the way throughout. Oh, I keep forgetting I've got all these things on here. There we go. Yeah, this is all stuff that I said. Okay. Okay. All right. So just to summarize, here we've got our sun. It's one of the lower main sequence stars. It's got a radiative core, convection on the outside, and energy is generated through the proton-proton cycle. or proton-proton chain. These upper main sequence stars are going to be convection core, radiation on the outside, and they are going to have carbon, nitrogen, oxygen cycles to produce their energy. Okay, let's get into the Orion Nebula. We all know about the Orion constellation. Okay, here's our Orion constellation. Here's his belt. It's hanging down. Right? Okay, there's actually right here, I think it points it out. Yep, there we go. There, go back. All right, right here there is actually a very visible, very active star-forming region. Okay, this is the visible Orion Nebula, and it's only a small, teeny tiny part of a much larger, dusty molecular cloud. I think that's what it shows here. Okay, so it makes it bigger. Here's our dusty molecular cloud, and there are some brand new stars that are being formed in here. Okay, here's some wonderful pictures to show you. Here we go. All right, here we have the Beckman, I don't know how to say that, the BN object. The hot star is just getting ready to reach the main sequence part. And then we also have the KL cluster of cool young protostars, which are detectable only in infrared, and that would be, the KLs would be here, and the BN would be, well, I don't think we have one. That's okay. It's in there somewhere. Lots of things. Okay, these little ones are only detectable through IR or infrared. This one here, being a main sequence star, it's one that's visible through visible light. All right, so let's see what else we have. Ionization by ultraviolet photons from the hottest stars is lighting up the nebula and making it glow brightly. And then many stars visible in the Orion Nebula are surrounded by disks of dust and gas. And these disks don't last long, and the disks give us evidence that the stars are extremely young. Okay. And all right, that's it. So I guess I'll see you in class.